Excuse me, ma'am. Can we start, ma'am?
Yeah,
Yes, ma'am. Good morning, everyone, and welcome back to day three of our 12 days refresher course on wireless communication. Our first session today is on digital modulation techniques, MRA PSK and MRA QAM. To begin with, I would like to introduce the speaker of this session, Dr. M. Meenakshi. Dr. M. Meenakshi is a professor with the Department of Electronics and Communication Engineering at College of Engineering, Guindy. She received her ME and PhD degrees from Anna University. Her research interests include various aspects of wireless communication, especially wireless and optical communication, design and optimization of optical interconnect transceivers, ultra-wideband communication system design, material distributive topology-based antenna design optimization, hybrid FSO or millimeter wave and millimeter wave beamforming, lightweight cryptography and side channel analysis, and 5G wireless communication. She has authored or co-authored over 80 plus technical papers. We are happy to have you, ma'am. Thank you for joining us. Over to you, ma'am.
yeah. Thank you. And I will also place my thanks to Professor Selvaraj and the institution for having me here. Thank you very much.
Thank you, ma'am.
Uh, good morning to all. Uh, the topic which I'm going to be dealing with today is on digital modulation techniques. Uh, we particularly to be focusing on the Emery PSK and the MQAM, both these schemes being the most implemented schemes in wireless systems. Okay. So, as a precursor, we need to know in a wireless communication system where do these things fit in the overall structure of a wireless communication system. Okay, so I'm showing you here a typical structure or configuration of a wireless communication system or a wireless interface that is going to be a part of any of the devices that are uh, capable of communicating in the wireless domain. For example, you have your Wi-Fi, you have your cellular phones, you have your Bluetooth devices, you have your Zigbee devices, LoRa devices, you have any number of technologies currently available for wireless communication. So all those communication devices are definitely, they need to have a wireless interface, communication interface, and that in addition to processing. So basically, all these devices, your Raspberry Pi or whatever, they do have a processor for carrying out algorithms, user-specific application-related algorithms and processing and so on. But then, if they are communication capable, they need to have this wireless communication interface. So, leaving off all the base processing that happens in the digital domain, depending on the application needs. Okay, coming to the communication interface. So broadly, we can split this communication part into two parts. So one is the processing that happens on your baseband signal. Okay. So your baseband signal is your application signal, but it could be the voice signal or a video signal or data signal or whatever. Okay. So or sensed signal if it is a small sensor on an IoT device and so on. Okay, so that application bandwidth, whatever processing we do at the baseband level itself, within that application bandwidth itself, so that we call it all that processing we call as the baseband processing, and then the signal cannot be transmitted over a wireless channel in the baseband itself. For example, you take your voice signal, we kind of restrict the transmission, I mean the voice signals to say 4 kilohertz bandwidth, okay, for voice communication. If it is going to be music or something, we try to take in the entire band of 20 kilohertz of audio signal. But if it is voice, we try to restrict around 4 kilohertz, less than 4 kilohertz, and so on, and then do A to D conversion and then transmission and so on. Okay, so that would be the bandwidth over which, or the ADC converted bandwidth, that is the bandwidth over which the baseband processing will happen. Okay, but this signal, baseband signal, cannot be transmitted over a wireless channel as it is. We all know that there is always, whenever you want to send something out in space, you definitely need a carrier, a higher frequency signal that can carry your information in some form. And that process of mapping your baseband information onto the carrier frequency, which can actually carry your signal across the wireless space. Okay, so that process is what we call modulation. Okay, so we have all this baseband processing happening in the baseband, and the you need to do translate it. You need to take the signal from baseband to the band pass domain. Okay, so that part is done by what you call as the RF front end, or your band pass section of your transceiver, or so there are different names to that, or the analog front end, and so these are all different names given to this up conversion, the translation that is going to happen from your baseband signal spectrum to the band pass spectrum. So band pass spectrum is nothing but your baseband signal centered around a certain carrier frequency, which is allocated by, if it is cellular system, this carrier would be allocated by the operator. If it is a broadcast system, you have specific carriers depending on the application or depending on the channel and so on. So the baseband accordingly would be mapped to the particular carrier. In satellite links, again, you have these frequencies that are all already licensed for operation in specific bands. So depending on which satellite or which frequency band is used, accordingly, the baseband signal will be translated to that respective carrier frequency band. Okay. So so within this, what happens? Where is your actual modulation coming in, right? So the modulation process, which essentially translates your baseband signals onto an RF carrier, okay, or in digital modulation, your baseband is all represented in the form of bit sequences. So your modulation is nothing but mapping these bit sequences or combination bits, which we also call as symbols, mapping these symbols to the carrier. Okay, so that process is called as your modulation process. And this process doesn't happen within the baseband or within the analog front end. So partially it happens in the baseband and partially it happens in the analog front end. Okay. So that's why I am trying to highlight about both these aspects here. Oh, so in baseband, where does it fit in? So you can see here, I have given a diagram corresponding to what happens in an overall digital communication system. So, and whatever I have given here is the different architectures for, on the left hand side, whatever I have given, they are the different architectures for the analog front end. Okay, so it can be a heterodyne architecture, which you may be aware of, heterodyne, super heterodyne, those kind of architectures, where your your baseband signal gets up converted to an intermediate frequency, and then from intermediate frequency gets up converted to the required radio frequency. Alternately, there is also the architecture which is called as the direct up conversion or direct down conversion, wherein the baseband directly gets translated to the desired radio frequency signal. So this is based on the analog front end or your RF front end. Okay, so these are some typical architectures which can be used for the upconversion process. And coming to the baseband, let's move to the next slide here, which kind of gives an elaborate version of what to do in the baseband. So in baseband, you have your signals data that is coming in. Most of your, for the current scenario in our wireless devices, our information is coming in digital domain in the form of ones and zeros, which are mapped into some positive and negative amplitudes. Okay, depending on the logic that is used, it's mapped to certain amplitude levels. Okay, and in case, okay, your information is not coming in digital form, then you need to do an analog to digital conversion process, and we know that this involves using the anti-aliasing filter, sampling, quantization, and then encoding. So using these processes, we try to convert your analog signal to a digital signal. The analog signal which you're talking about is the user input signal. Okay. So currently, this kind of is mostly used in say sensors or wherever you're capturing analog signals from the sensing unit or wherever, and then you are converting it to the digital domain so that it can be further processed within the device, and then subsequently transmitted to any other base station or any other sync module and so on. Okay. So this analog to digital conversion comes at the data acquisition point, wherever you are trying to acquire data for further processing. Okay. So assuming we have your processed digital of a digital communication system is the channel encoding process. Okay. So what we understand that is channel encoding. So we are trying to encode this digital data to a form that will be that will help the at the end, at the receiver end, it will help us to identify if some errors have happened on your data, and if so, sometimes it's also possible to correct the data depending on what kind of channel encoding scheme, channel coder scheme you're using. We may be able to identify if there are any errors in the transmitted data and also correct some of those errors. Okay, and errors normally creep in on your data because, as I mentioned earlier, they are going in the form of signals, analog signals. After the analog front end, your signal goes in the form of analog signals, okay, analog carrier modulated signals. So they may come across a lot of fading and distortions in terms of additive or subtractive noises. And finally, when it enters the receiver, also the receiver is also an electronic circuit, and we know all electronic circuits generate noise, which we normally call as a thermal noise. It's a random thermal noise. Okay, so all these noises put together are going to impact your signal that is going to get transmitted. So when you try to decode or demodulate and decode that signal, your data bit which you finally identify is not going to be same as the original data bit that was transmitted. Okay, because of all these impairments that are happening in the channel, as well as because of the noises generated in your receiver circuitry and so on. Okay, so we need some mechanism by which we can identify if there are any errors, and if there are errors, we should also be able to correct those errors. Maybe not all of them. How many errors can be corrected will depend on capability of this channel coding scheme that you're using. But you take up any wireless communication system, you will definitely have your digital information that is coming in after all the processing will first be channel coded. Channel coding is an essential part of any communication system, digital communication system, including your wireless communication system. Okay. So after doing this channel coding is also called as error control coding. Some of the examples are your Hamming code, your convolutional coder, your turbo coding schemes, your LDPC coding schemes, your Pola coding schemes. They are all examples for channel coding schemes. So subsequent to that, if necessary, we could multiplex multiple user signals or multiple application signals, and then it will follow through line coding, which is also again optional. And then you have your basically line coding gives you amplitude mapping as well, level mapping as well as timing mapping that is provided by the line coding scheme. And then you have in the baseband, you have what we call as a baseband modulator. It is also called as a transmission encoder. So this essentially maps your data bits that are coming in into appropriate modulation symbols, but in the baseband itself. If you look at the spectrum, that will be in the baseband spectrum. Okay, so this mapping of your input symbols to modulated symbols in the baseband, okay, that is done by this baseband modulator. And of course, we also do what is called as pulse shaping. And pulse shaping is that you're going to shape the envelope of your modulation signals, and this is done in order to avoid any intersymbol interferences between the symbols from the same source. Okay, so this is the shaping induced, the envelope shape induced intersymbol interference. Okay, so that is addressed using pulse shaping filters, and then we do this the baseband modulation. Then we do what is called as the up conversion, where you translate your baseband modulated symbols to the desired carrier frequency using this band pass modulator. So this band pass modulator is actually part of your this portion, your analog front end. Okay, so this is where you do the band pass translation. So that is shown here. So you have your INQ. This INQ are the ones that are going to come from your baseband, and this INQ is nothing but the real part and the imaginary part of the complex baseband symbol that comes out from the baseband modulator. We'll see in detail what these I and Q are. And we name them as I and Q because they are going to, this real part of the complex baseband symbol is going to modulate the cosine of the carrier. Suppose FC is the carrier, RF carrier on which your information needs to get transmitted. The in phase, this real part of your complex baseband will modulate the cosine of the carrier, and the complex part of your baseband symbol will modulate the sinusoid or the quadrature of the carrier, sign of the carrier which you have identified. And that will be combined appropriately, and then it will undergo all the subsequent process of amplification and then filtering, and then it goes through the radiation subsystem, which is the antenna subsystem, into the wireless space. Okay, so that's the band pass. This is the modulation that is happening in the band pass domain. Okay, so you have modulation mapping done in baseband domain as well as band pass domain. So how are we getting this I and Q for the based on the kind of modulation you are going to have? So they all these things will be seen subsequently, and how this is obtained for the MPSK and QAM to be implemented in your system. Okay, so that will be the focus in this particular topic. Yeah. So I had mentioned here about the quadrature modulation. The quadrature modulation is nothing but whatever I mentioned now, the baseband I information, which is nothing but the real part of the baseband complex symbol, and Q represents the imaginary part of the baseband complex symbol, which comes out from your baseband modulation mapping. Okay, so that in phase, it's also called as the in phase baseband signal. This modulates, as I mentioned, the cosine of the carrier, and this modulates, the Q modulates the sine of the carrier, and they are combined in this form in order to generate your band pass modulated signal. Okay, that goes through the channel. So essentially, the characteristics of the baseband, spectral characteristics of the baseband, do not change because you are doing your this when you do this band pass translation. So if you look at the one-sided bandwidth, so here the baseband is from 0 to some frequency maybe. So you can see that this remains intact here from 0 to the whatever was the baseband frequency. So it's remaining in the same band. And what you see is the reflection here because we have translated to an higher frequency. So you see the spectrum or the double-sided spectrum. So that's what you are going to be observing. But if you look at one side, the baseband is exactly same as what you had in the spectrum you had for your baseband IQ signals. So that's what this is called as the quadrature modulation, because you're using the in phase of the carrier and quadrature of the carrier in order to map your modulation symbols to the RF desired RF carrier. Okay, so this is the quadrature modulation, and we do after signal gets transmitted over the channel and then finally receiving it back on the receiver at the receiving side using an appropriate. So this is the receiver part. You can see there will be a band pass filter which will avoid all the other unnecessary signals and take in only the desired spectral band. And then you will have what is called as a low noise amplifier because we have to reduce the noise that gets introduced by a receiver circuitry. So, but at the same time, want to amplify the desired signal. So the first component here, subsequent to the band pass filter, is a low noise amplifier. And of course, following which you have the down conversion using the desired carrier frequency, and of course you have brought your signal to the baseband here, so use a low pass filter to further reduce any noise levels, and then take your INQ. Okay, the INQ symbols are taken in for the reception process. Okay, so this portion wherein you are down converting again using the in phase carrier and the quadrature carrier to bring your modulated signal to the baseband is what you call as the quadrature demodulation. So this process is shown here in a little bit elaborated. So the in-phase carrier, after all the whatever the processing I mentioned in the analog front end, low noise amplification and so on, we down convert using the in-phase carrier and the quadrature carrier and filter it and extract the INQ symbols, the received INQ symbols. Okay, INQ baseband information, and your baseband symbol is nothing but the I plus JQ. That's your baseband symbol, which will be further processed to determine what is the bit combination that was transmitted using this INQ and what you have currently received now. Okay, so so this IQ modulated demodulated is an essential part which we need to clearly have an idea about in the practical implementation of modulation schemes. Okay, so with this little bit of information about how things are actually used in a practical system, let us go to the theory of this modulation. So essentially, modulation is where we try to map your bits to a signal. Okay, so your bits which are defining your logical entities, logical ones and zeros, they are mapped to certain amplitudes and timing with some timing information. Okay, the timing is to say this bit exists over this duration, and that duration normally call it as the bit duration. Okay, and number of bits together can form one symbol, and that total duration we call it as a symbol duration. Okay, and looking at the binary modulation, so assuming a bit is going to is going to modulate a carrier, basically we exploit the characteristics of the carrier signal. So popularly we use sinusoid signals for carrier, generate sinusoid signals for the carrier. So looking at the properties or the characteristics of the sinusoid, there are three characteristics which can be changed in order to realize your modulation. Okay, so one is you can change the amplitude of the carrier, or you can change the phase of the carrier, or you can change the frequency of the carrier, or you can change some combination of these parameters in order to realize your modulation. So for binary, if you see amplitude, so then you shift between two amplitudes. For a 0 bit, you could have zero, no carrier, and for a 1 bit, you can have a carrier. So this is one special case of ASK, which we also call it as on-off key. So whenever you don't have, when you have a 0 bit, you don't have the carrier. Whenever there is a 1 bit, you have the carrier. So it's like switching on and off. Okay, but most prevalently, defined ASK is to define two different amplitudes for the carrier for the 0 and the 1 bit. Okay, so that's your ASK. And PSK is where you can define the phase shift. So now you can see that whenever the phase of the signal is 0 with reference to the phase at time t equal to 0, we can map it to 0 binary data. And whenever the phase of the signal um, reference to the phase at time t equal to 0 is when the phase shift is going to be 180 degree, then we call it as a binary 1. So it can be the other way also. 0 can be represented as 180 degree phase shift, 1 can be represented as 0 phase shift with reference to the phase, the initial phase. Okay. So that wherein, so we are introducing a change in phase of the signal based on the bit information. So that is your BPSK or binary phase shift keying. Or whenever we change the phase of the the carrier based on the information, then we say it is a phase shift keying scheme. Since we are switching between phases over different symbol durations, we call it as phase shift keying. Okay. And similarly, if you work on the frequency of the carrier, suppose you have the 1 bit is represented by a lower frequency carrier, and a 0 bit represented by a low frequency carrier, and 1 bit represented by a high frequency carrier. These two frequencies are shifted versions of the actual carrier frequency you're using. Okay, suppose FC is your carrier, so for a 0 bit, you'll be shifting from FC to FC minus del F. For a 1 bit, you will shift from to FC plus del F. Okay, so from the assigned carrier FC, you'll be shifting FC minus del F or FC plus del F. So the two frequencies which you may observe on the channel when the signal goes on the channel is your FC minus del F and FC plus del F, depending on the bit being a 0 or a 1. So you can see in this picture, you can see a low frequency signal and a high frequency signal, okay, corresponding to the 0 bit and the 1 bit. Okay, so these are all binary, what was shown here are for binary transmission. But same thing applies for Emery schemes also, wherein we'll be considering, so M represents the number of possible signals, modulated signals that can be transmitted in the particular scheme. Okay, so suppose M is 16. Okay, so I say I'm considering an Emery modulation with M value of 16. Okay, that means there are 16 possible signals, modulation signals that can be transmitted into the channel. Okay, that can be used in that particular system. So 16, so since I have 16 possible signals, that means I can transmit 16 possible symbols. So these symbols are nothing but combination of, each symbol is nothing but a combination of bit. Okay. So now when I have 16 possibilities, that means I can consider 4 bit as one symbol. So with 4 bit, I can have 16 possibilities, and each of this the possible combination of bits can be mapped to one modulation signal. So I have 16 possible bit combinations, I have 4 bit combinations, and I have 16 possible signals, and we have a 1:1 mapping between this bit combination and the signal, and that can the signaling waveform. So that modulation, we call it as an Emery modulation. So I can extend the same concepts of ASK, PSK, or FSK to these higher order modulations. These are called as higher order modulations. So the same 16 case, now if I want to implement it as a 16-array ASK, then I should define modulation signals, carrier signals, with 16 possible amplitudes. Then I'll be mapping this 4-bit combination of symbols to this uh, 16 possible amplitude signals. Okay, but generally ASK is not not preferred in practical systems because they are more affected by noise which is adding in the system. Okay, so we normally don't prefer ASK, similar to the explanation we give for not preferring amplitude modulation, because noise or fading also affects the amplitude of the signal. So it will be difficult at the receiver to identify whether the amplitude that is change that is happening is because of the symbol change or because of noise and fading. Okay, so we don't prefer ASK schemes. Applying or considering Emery PSK, then you have m possible m possible signals at some frequency fc, but these m possible signals are all differing in the phase. You know that you can write the signal as some a cos 2 pi fct plus theta. Okay, so a represents the amplitude, the fc is the carrier, and you have a theta term there. So in the case of Emery PSK or 16 PSK, you will be having 16 possible theta values. Okay, that you would be identifying, and corresponding to the bit combination, 4-bit combination, you'll be selecting any one of this theta, and that particular signal would be transmitted through the channel during that symbol duration. Okay, so that is the extension of your PSK to Emery concept. Similarly, in Emery FSK, you'll be defining m possible frequencies centered around your FC, your carrier frequency, and based on the 4-bit combination, you will identify a particular frequency, and the FC term will get modified. FC will be FC plus del F minus del F, like that. It will be the shifted version of your FC, shifted carrier on your FC, which will be decided by your bit combination, and there could be any one of 16 frequencies that may be getting transmitted over the channel. So that's your Emery FSK. So these are the basic ways in which you can do modulation, and you can extend it to the Emery scenario, considering more number of amplitudes or more number of phase shifts or more number of frequency possibilities. Okay, frequency shifts. Okay, and there is also another thing that we will go elaborate on these the MPSK and NFAM as we go further. I'll also say what is NFAM. NFAM is nothing but it's a hybrid of amplitude and phase shifting. Okay, so we'll be considering combinations of amplitude and phase. Both A will change and theta will also change. So we'll consider combinations of A and theta and work out some 16 possibilities in the current example of 16 array. If it is 256 array, then we work out some 256 possibilities of amplitude and phase. And such a modulation, which is a hybrid modulation between ASK and PSK, we call it as the Emery quadrature amplitude modulation. Okay, so that's the name given to that particular modulation, right? So, and I have also, if you see, I have mentioned another CPFSK. Okay, so I've shown explained to you FSK here, which you can also extend over multiple frequencies. What you mean by CP is that continuous phase. The CP stands for continuous phase. So as you can see here, between the shift from low frequency to high frequency. I hope you're able to see my cursor on the screen. Participants, can any one of you reply to that?
Yes, ma'am.
Yeah, okay. So as you can see here, we are shifting from here for a 0 bit, we have a low frequency, and then for 1 bit, we are having a higher frequency. And you can see that the phase, unlike this case where the phase is suddenly changing, you can see the phase is suddenly changing. Unlike that, you see that there is no sudden phase changes happening here when you're switching from one frequency to the other frequency. The phase remains continuous. Okay. So this kind of a realization implementation happens through a specific way of doing things. Okay, and that is the most popular methodology for implementing memory FSK schemes. So that is called as continuous phase FSK, CPFSK. Okay, so we are not going to be focusing on this because of certain reasons. Our focus for wireless channels is primarily this MPSK and MQAM. Okay, and this n value in practical systems today can go up to 2048. Okay, as per the standards which you look for Wi-Fi and your cellular systems, it can go up to 2048 in some of the latest standards which are getting introduced. Okay, and then there is also two other things which we need to know. Another thing which you need to know regarding modulation, that is whether you are doing a coherent detection or a non-coherent detection. So what do you mean by this coherent or non-coherent detection? So when you get back here, I'll just go back to this slide here. Sorry, your quadrature modulator. Okay, so you have your RF signal which got transmitted after up conversion of this baseband using a oscillator here, an in phase and a quadrature, a local oscillator here, LO here. So after up conversion, okay, you had generated this signal. So this signal travels through the wireless space, okay, and this has to get down converted here at the receiver end. Again, at the receiver end, you have a similar local oscillator, an oscillator which you normally call as the local LO, which is generating this cos 2pi FCT and sin 2pi FCT. Okay, at the receiver end. Now the transmitter is in some location, receiver is in some other location, and this is a different oscillator, this is a different oscillator, but they are both generating cos 2pi FCT and sin 2pi FCT. So the signal which modulated this carrier, the in phase and quadrature carriers from this LO would be coming from a distance, and in the process it may undergo there will be some propagation delay is there, and there are some phase offsets that may be generated in the channel. And when this signal comes here and you try to correlate, okay, so this signal will be coming with say cos 2pi FCT plus some phi, some phase offset would be there, okay, because it is propagating over a long distance, and there could be a lot of impairments that could affect the phase of the incoming carrier modulated signal. So this when this comes in, this will be coming as cos 2pi FCT plus phi. That it will be coming with the phase difference compared to the locally generated in phase carrier. Similarly, the quadrature component of this will be coming as sin 2pi FCT plus phi, which is slightly phase different, having a phase difference with respect to the locally generated quadrature carrier. So there is a phi phase difference existing between the incoming signal and the local oscillator generated signal here. Okay. Now, if we take some efforts at the receiver to identify this phi, estimate this phase, and then nullify them or synchronize this LO along with this, okay, this incoming signal, so that both of them are going to be in the same phase. Okay, so doing this phi, estimating this phase, recovering this phase, and then aligning the incoming incoming signal carrier to the local oscillator signal here. Okay, local oscillator generated in phase and quadrature carriers. Okay, aligning them in phase. That means making them in phase, co-phasing them by properly estimating what this phi value is. Okay, so if the receiver makes that effort, or we have a mechanism to estimate this carrier or recover this carrier phase, and then align the incoming signal carrier with the locally generated carrier, then we say that is a coherent way of implementing your detection. We can call that kind of a receiver as a coherent receiver, and the detector we call it as a coherent detector. Okay. Suppose I'm not doing those kind of special efforts. I go ahead with this is phase shifted. There's a received signal having a small phase offset with respect to the locally generated carrier here. Okay, we go ahead with the processing without taking care of that phase offset that is present between the incoming carrier and the locally generated carrier. And such a receiver, we call it as a non-coherent receiver. So that is what I have mentioned here. If you are able to get the phase locking between the incoming signal and the locally generated carrier, then we say it's a coherent mechanism, coherent detection mechanism. Definitely, the signal to noise ratio, the signal performance, SNR performance is much better when you use a coherent detection because you're doing phase matching and then going ahead with the rest of the process. Whereas in non-coherent detection, we are not doing this phase matching. Because you're not doing that, it is less complex, but the SNR is not that good, and as a result, it has an inferior error performance. By doing this coherent detection, you're able to improve the SNR by at least 2 times. Okay, so your signal power doubles with respect to the noise. Compared to the case where you are not doing any phase recovery and phase locking. So compared to whatever SNR you may get here, the SNR you may get here is going to be double. Okay, so that's a big boost to use coherent detection schemes. Okay. So keeping that in mind, now let us come to the model of a wireless communication system. So you have, say, your SI of t is the transmitted signal at any instant of time, and not in a normal system where we are not bringing the wireless component, we will have noise adding from the channel or from the receiver or from any of the other sources. Put together, we can characterize that noise as AWGN, additive white Gaussian noise. So the normal model which we consider, communication model which we consider, we normally say that the received signal is nothing but the transmit signal plus noise. But in a wireless communication, because you have multipath propagation, you also have a distortion called as fading that impacts your signal. And this fading is multiplicative in nature. Okay, so you represent the fading effect as alpha here. So your received signal model is now alpha into SI of t. Okay, this alpha is a non-negative value. Okay, so alpha into SI of t. So this is a multiplicative noise which increases your received signal strength or decreases your signal strength based on constructive interference or destructive interference of the multipath signals which are being received at the receiver end. Plus, of course, the noise, additive white Gaussian noise. Okay, so this is your signal model for a wireless communication system. So we need to take into account this fading, multiplicative fading effect also. So that would be taken into consideration in modeling this communication channel. And coming to a simplified structure of what happens in the modulator, as earlier I had indicated, the modulation is done in 2 steps. One is the symbol to baseband complex symbol mapping. Okay, so let me go back to the same diagram here. So from your baseband symbol to the baseband complex symbol. Baseband complex symbol is the I plus JQ. Getting from your bit combination. A bit combination for the 16 array would be 4-bit combination. That can be 1000 or 1001 or 1111, whatever. So based on the bit combination, what should be the corresponding I plus JQ? Okay, so that is the modulation mapping we do in baseband. And then we have from baseband to the RF part, that is the up conversion, that is the band pass modulation part. Okay, so how we get this 2 steps, how do we go about, that is indicated here. Okay, So you have your, assuming we are doing all the other prior processes like channel coding, multiplexing, whatever you want to do earlier, assuming you are doing all of that, okay, and you have your message that is coming in. By message here we are meaning the ones and zeros, okay, that are coming in. And assuming you are doing an memory, you will have bit combinations that are coming in here as messages. And based on the message, now we have to identify a baseband complex symbol. Okay, so that part is called as the signal transmission encoder, and from the baseband I in Q, you up convert to the desired modulated signal. That is your bandpass up conversion process. Okay, or what the modulation done in the RF front end. Okay, now essentially what I need is I need forgive this arrow. I just there's a small this arrow should be pointed here to this portion, okay, and this arrow should be pointed here, so there is a small mistake here, forget about this. So essentially in modulation I need from MJ, I need to go to this modulation signal, so that is shown in this table. So for suppose your modulation is a QPSK modulation, okay, so in QPSK there are 4 possible signals, and so we will consider 2-bit combinations as a symbol. So assuming these are the 2-bit combinations, we need to finally map them to any one of 4 signals which are going to be differing in phase. So that is what is indicated here. So you have 4 signals here with different phase shifts. Okay. So that depending on the symbol, the phase shift is need to be identified. So if this is 0 0, then this is 5 1, this is 0 1, this is 5 2, and so on. Okay, for the carrier. Now this is done in 2 steps as indicated. So from 0 0, I need to get the baseband complex symbol mapping. And once I have the baseband symbol mapping, then this A will modulate cosine of the carrier. B will this complex the imaginary part will modulate the sine of the carrier, and when you combine them, you will get A cos 2 pi FCT plus one of the phase shifts. As I have given taken example phase shift as 0, 90, 180, and 270. So you need to get this. So this you have to get this baseband equivalent, and then from the baseband equivalent, you can up convert and get the bandpass energy signal, which is going to actually go through the channel. And now the reverse also the same thing will happen. So this portion of up conversion is what is shown here. I already earlier also I showed you as the IQ modulator, and this portion how to get this from the bit combination, how to get this complex baseband. Okay, so that is going to be simple mapping. So we will identify for 0 0 this should be the complex baseband, for this is a complex baseband, and so on. But using this real part and imaginary part, you should get the signal. So that means you need to identify the real part and imaginary part of your complex baseband from your modulation signal. Suppose you have identified these as your modulation signals, then from this you should find out what this real part should be and what this imaginary part should be in the baseband. Okay, so same applies for any higher order modulations also for PSK or ASK or FSK schemes. What we need to know is what are all the possible signals, energy signals that will get transmitted depending on the modulation which you're trying to use. Okay, and of course the reverse thing will happen here. So the down conversion from the analog to the digital domains will get a received complex value will get here, and from this you will try to identify what the message, that is the reverse process. If you're getting this, then you have to identify, okay, this corresponds to this complex number corresponds to this particular symbol. So that D mapping is decoding is represented here. So we say this is an estimate because the received signal, because of this kind of a channel, because of alpha and n of t would be noisy, and from this noisy you are extracting some complex symbol. This complex symbol may not be exactly what you're expecting, but a noisy version. So it will be a modified noisy version of A and noisy version of the 0. That is what you will receive. And from that, the decoder has to estimate whether it is corresponding to 0 0 or 0 1 or 1 1 or 1 0. Okay. So now the question is, how you relate these two? How do you get the relationship between these two, or how you get your complex baseband from this complex real-time energy signal? The real energy signal is a complex signal. So knowing your modulation. Okay, so right. So knowing your signals, okay, you can find out we can find out the basis signals or reference signals which can be used for representing your modulation signals in what you call as a geometric space. Okay, so using the geometric representation, if you know what are all your modulation signals, we can identify what are the equivalent axes if you want to represent them on a geometric space. And fortunately, there are definite procedures for that. And fortunately, for our all the popular communication modulation schemes which we use, most of them have the cosine of carrier and sine of the carrier as the basis, and so that simplifies the job of identifying the basis. And so phi1 of 2, phi2 of 2 are nothing but root of 2 by t cos 2 pi f ct and root of 2 by t cos sine 2 pi f ct. And this t is nothing but the symbol duration which you're considering. And this signal we consider over a period of one symbol duration. And this are mapped as the axis for your signal constellation. And with respect to axis, we want to place the signal now on this geometric space. And in order to do that, we try to identify what is the projection of the signal S1 of t on phi1 basis, that is done using this equation. Okay, and you will get S11, and when you try to project this S1 along the phi2 basis, you will do integrating 0 to t S1 of t into phi2 of t dt. That will give you S12. This S1 S12 are nothing but the coordinates of the signal in this geometric space. Okay, so for this signal you will get the coordinates is 0 0, and so this is where your signal will lie. Okay, S11, S12 will be 0 0, so this is where you will be putting that signal. And your baseband complex signal symbol is nothing but writing this coordinate in the form of a complex entity. Okay, so this first coordinate point is your real part, and the second coordinate point is your imaginary part, because this first coordinate has been obtained by projecting signal onto the cosine axis, which is not cosine of the carrier, which is nothing but the in phase axis. Okay, and the second coordinate value got it by projecting the signal onto the quadrature carrier. Okay, so we call this real part as the in phase complex baseband, and this is the quadrature complex imaginary part of the complex baseband. So with this, I can formulate my complex baseband symbol. I need these coordinates for my signals. Okay, so again, this can be projected to any order modulation and any kind of modulation. The same concepts can be applied. Only thing we need to correctly, for the given signals, what should be the basis signal that need to be correctly identified. And basis signals are representative of the axis of your geometric space. And you can see this by representing this kind of axis, you also are able to understand that these two bases are orthogonal to each other. That's why you have projected it like the orthogonal axis in the geometric space. Okay, and they will also carry unit energy. The energy of the signals would be 1. Okay, so so by projecting your desired signals onto the bases, you'll be able to identify where do they lie in this geometric space, and their location in the geometric space is represented by the coordinates. And the coordinates are nothing but the in phase and the quadrature, or the imaginary and real and the imaginary part of the complex baseband signal. Okay, so knowing this, we straight away can go for generating your signal by multiplying the SI1 coordinate, the first coordinate corresponding to the phi1 basis is multiplied with phi1, the second coordinate multiplied with phi2. If it is a general structure, you may have n number of bases, so you will multiply each of the coordinate with the respective bases and then combine all of them. But as I had shown you earlier, most of our modulation schemes require only the in phase basis and the quadrature basis, so it will be only two. You'll have only two of them, multiplying with the cosine of the carrier and sine of the carrier, and then combining that. That's your IQ. So that's how you generate your modulated signals. On the receiver side, the received signal you again correlate with the in-phase basis, correlate with the quadrature basis, and then you do the low-pass filtering, which is something but an integration to find out what is this projection, okay, along the basis of the received signal, along in-phase basis and the quadrature basis. But under an ideal case of this being SI1 and SI2, you will get SI1 and SI2 here. But you know that noise and fading impacts your signal, so you get a modified value here. Whatever you receive here is a noisy version of what you transmitted I. It's going to be I dash, which is a noisy version of I, transmitted I. Similarly, the Q you had transmitted, this will be a noisy version of the Q, some Q dash, which is a noisy version of Q. Okay, so this is a simple methodology of getting the from the baseband, from the signal, okay, from the desired signal, okay, for the responding to the modulation, how you try to get the baseband complex symbols, and knowing the baseband complex symbols, how you are able to actually go forward generating your modulation signals and so on. So once you know for each of the signals what is the coordinate, I can straight away do the mapping of my this previous step. Okay, mapping. So this I have obtained now. So the mapping of the symbol to the signal can be done. So that is straight away 1:1. We can do the mapping. No problem about that. Okay, so getting the complex baseband from the modulation signals is a very crucial step. You have to do it correctly, so that you are going to generate the same signal when you are doing the quadrature modulation. I hope it's clear up to this point. Okay. So now, extending this further, now we can have similarly you can obtain the transfer baseband signals for any of the modulations. So this is an example of a QPSK scheme. This is an example of 16 QAM scheme, and so on. So what I wanted to show here is your transmit signal is represented by a point in the signal constellation, but the received signals, when you plot it in the signal constellation, you can see that they are all going to be placed at around in and around your respective signals. That means the noise is disturbing the location of the received symbols, as mathematically I had shown in the earlier slide. Okay, so how much is this noise going to impact one of the important performance of the modulation scheme? Basically, you try to see the scheme is working well or not based on the bit error rate or the probability of error. So if I transmit this symbol, okay, and but when I decode at the receiver end, suppose my decoder says that the transmitted symbol is this, signal is this, then that means that an error has happened. So how much, when error will happen? When the amount of noise, okay, the amount of displacement that is caused by noise, okay, it takes your signal from this space to this location. Okay, so here as it is shown here, the geometric space is divided into 4 regions. So as long as the received signal lies within this region, the receiver will always map it to this particular symbol. But if the noise is going to take a signal beyond this boundaries, then it may be decoded as a different symbol, okay, which we normally call it as an error having happened. Okay, so that is what is depicted here. The probability of error is nothing but when X does not lie in the respective zone corresponding to MI when MI was sent. Okay, so that can be computed as the probability of error. I'll not go into detail about all of this. One thing I would like to say is that this probability of error, we can get an assessment of this probability of error if we have an idea of how much noise is there in the system which we are considering, and what is the DIK. DIK is nothing but the distance between two signals, okay, or the closest signals in the signal constellation. So now if you take up this constellation, this is called as a signal constellation. So we look at the closest distance between any two. Now we take any two signals here. Okay, they are. This is the closest distance you see between the two signals. That distance is called as the minimum Euclidean distance because it is distance between signals, and that comes in the expression for the error, probability of error. Okay, so that comes here, so that you can just keep in mind. So this DIK is nothing but the minimum distance between signal points in a constellation. Now, in the case of QAM, the minimum distance is between 2 points which are occurring linearly, okay, either this way or this way. The diagonal distance is going to be larger, so the minimum distance is this distance. Okay, so that would be defining from the signal constellation. You can identify the minimum distance that could be used here in order to find out what is the probability of error. So you need to know the mean distance from the constellation and also the amount of noise which is going to be impacting in the system. Okay. So a simple QPSK transmitter. For QPSK, there are only 4 possible symbols, and we can treat it like like 2 binary schemes, and so we can do a serial to parallel here, or split the odd and the even bits separately. The odd bit will multiply the sign of the carrier or the phi 1 of t. The even bit multiplies the sign of the carrier, and then you combine them to generate your QPSK signal, which will depict the 4 possible phase shifts. So I'm just showing you this is what happens in one of the arms, the upper arm. So you can see it's like binary. There are only 180-degree phase shifts that are happening here. And similarly, in the lower arm also, you're seeing only 180-degree phase shifts that are happening. But when you combine both of them, okay, so this is the in-phase part and this is the quadrature part. When you combine both of them, you can see that the other phase shifts are also reflecting on your signal. For QPSK, you have four possible phase shifts. It could be 0, 90, 180, 270, or 45, 135, minus 135, minus 145, minus 45. So like that, 4 possible phase shifts can be defined. So your modulated signals should reflect those possible phase shifts based on the information symbols. The information symbols are given here. Okay, and just as an example is given here. Okay, now this is your PSK. So similarly, we will extend this to higher order PSK schemes. So we will be doing the in phase. We will be doing some modulation, and quadrature phase also quadrature also carrier also may be modulated. And when you combine them, your resultant modulation signal should reflect the n possible phase shifts depending on the input pattern. Okay, so implementation wise, the same thing holds good for whether it is MPSK or MQAM or MFSK or whatever. Okay. So only thing that's going to differ is the constellation. So how is the signal constellation? For QPSK, we saw there are 4 points in the signal constellation. For MPSK, there are going to be n number of points in the signal constellation. For MQAM, also there are going to be n number of points in the signal constellation, which are all generated using the same methodology which I have indicated here. Okay. So now, so this is the receiver, the same with IQ mod, the same thing I have shown for the receiver here. So you correlate with the locally generated in-phase and quadrature carriers, which are all the bases, and then integrate to find out this x1, x2, which are the received I and received Q, which are a noisy version of the transmitted I and the transmitted Q. Okay, from that you find out whether based on sign of this, you can say whether it's a 1 or a 0, and then you can multiplex. So in QPSK, this job is simpler because you can treat it like 2 BPSK streams. So you can just straight away go for getting back your symbols by individually using a decision device on each of the arms. But for a higher order modulation, we will be actually comparing the received vector with the possible transmission signal points. Based on the signal points, we'll compare and then we'll try to identify. Okay. So these are all some alternate versions of QPSK which have been used in practical systems. So this is your regular QPSK, and transitions, whatever is shown in arrows, are the possible transitions that can happen from one symbol to the next symbol. Okay, so that are allowed in the scheme. So as you can see here, 180-degree transitions are allowable here in the standard QPSK scheme. But when I say 180-degree, it also means that the transition, there is both the bits are changing. When both the bits are changing, there will be 180-degree transition happening here and 180-degree transition. In both places, there is 180-degree transition, and that in turn results in the envelope undergoing a zero crossing. So that will cause, when such signals go through nonlinear devices, it may cause some spectral expansions may be caused. So spreading may be caused. So side lobes may increase and so on. So in order to prevent that, there was a modified version of QPSK, which is called as offset QPSK, where we don't allow this simultaneous transmission of both the bits to change. So you can see here the transition is from 0 to 1, 0 to 1. Both bits are changing. The 0 to 1. Okay, the upper arm and lower arm in both there is a change that is happening. That is represented by the diagonal transition of 180-degree phase shift. Okay, so we don't allow that to happen in offset QPSK. If there is a 180-degree phase shift that needs to be done, we will either change this bit alone first. Okay, so thereby we will have this phase shift, and then we will change the other bit from -1 to 1, and so this is the path that will be taken. So only one bit will change phase at a time, and so we realize this over 2-bit intervals, or this change should happen within one symbol duration, but we do it over this change will happen over 1-bit interval, and this will happen during the 2nd-bit interval, and totally the symbol duration is 2-bit intervals. Okay, corresponding to the symbol duration of this 1-1-bit combination. Okay, so this is called as offset QPSK. So that kind of keeps your spectrum intact. And there is an alternate QPSK scheme, which is where we try to take two possible constellations. The green represents one constellation, the red represents another QPSK constellation. So over successive symbols that are coming in, QPSK symbols, or which are nothing but 2-bit symbols that are coming in, based on the 2-bit combinations, we need to select a phase shift. But here we will switch between the two signal constellations. Suppose I got a 0, at the beginning. So I'm first using this red constellation. So I'll be selecting this phase shift, 180-degree phase shift. During the next symbol instant, say I am again getting 0. So now I should not use the same constellation. I should use the green constellation, QPSK constellation, and see what is the symbol corresponding to 0, and then identify, consider that. Okay, so I think there is a mistake here. So I'll be selecting this point, which may correspond to the 0. Okay, so we need to keep switching between the constellations for successive symbols. Okay, this is called as pi/4 QPSK, because the two constellations are differing in phase by pi/4. Okay, so this kind of helps in because we are switching between constellations over over successive symbol periods. We can kind of do a differential decoding at the receiver, in the sense I can kind of look at the phase difference between successive received symbols, and based on that I'll be able to identify what my transmitted symbols are. Okay, so this is one modified version of QPSK, which has also been used in earlier standards. Okay, so because of that I just brought these two things into picture. And coming to our MPSK and MQAM now. So MPSK is treated as a linear modulation scheme, whereas Emery-QAM, MPSK and Emery-QAM are treated as linear modulation systems, whereas this CPFSK or Emery-FSK, that is treated as a constant envelope modulation scheme. As I shown you earlier, in anything in MPSK and MQAM, there is some slight variation that happens in the signal amplitude because of the instantaneous phase shifts that are happening. Whereas in continuous phase FSK, it is only the frequency that changes, and so there is no envelope. The envelope of the signal remains constant throughout. Okay, so that is categorized under constant envelope modulation. And coming to a bit more detail on your Emery PSK scheme. So your carrier is now going to have multiple possible phase shifts, or m possible phase shifts. These m possible phase shifts can be defined as 2 pi by m. The 2 pi is your 360 degree. Okay, so within this 360 degree only you have to define the m different phase shifts. So we give an index here, I minus 1. So starting from 0, okay, when I equal to 1, the phase is 0. So we keep shifting by 2 pi by m across this 360 degree, and thereby we can define m different phase shifts. So equation wise, we say theta I, the ith phase shift is nothing but 2 into I minus 1 pi by m. Okay, so this you can write your modulated waveform as root of 2 ES by TS. ES is the energy of the symbol, TS is the duration of the symbol, and you can see that ES is nothing but the number of bits that are going to be there in the symbol times the energy which is spent per bit. Okay, energy which you are using per bit. So per bit energy into that, may how many bits constitute a symbol. So if m is 16, then 4 bits will constitute a symbol. This 4, how we are obtaining this 4? It is nothing but log to the base 2 of m. Okay, so 4 times EV would be your bit energy in the case of 16 array modulation. Similarly, the symbol duration is nothing but log to the base 2 of n times TB. Okay, TB is 1 bit duration. 4 bits together forms one symbol. So 4 times TB is your symbol period. Okay, so in general it is log to the base 2 of n times TB. So you have your signal is written as root of 2 ES by TS. Cos 2 by FCT, carrier is the same, amplitude is the same, but the phase is depending on I, whether it's the ith signal or first signal or second or third or the nth signal, this I will vary, and accordingly the phase shift, you are able to get the different phase shifts, and that is your Emery PSK signal. Okay, the same thing in terms of the in-phase and quadrature carriers can be written as in the form of cos A plus B. You can write cos A cos B. You can use a trigonometric relationship and get it in the form of in relation to the cos 2 pi FCT and sin 2 pi FCT form. Okay, so now we are getting here as this term and this term in terms of the phase shift that you have here. Okay, so cos theta and sin theta terms, and you have the carrier term also, the in-phase carrier and the quadrature carrier term. So in this form, we have got your signals now. We can correlate with the basis. The basis here is going to be root of 2 by Ts cos 2 pi FCT and sine of root of 2 by Ts sin 2 pi FCT. They are going to be your basis signals. So in terms, by replacing the root of Ts into cos 2 pi FCT as phi 1 of t or the in-phase basis, and root of 2 by Ts into sin 2 pi FCT as the quadrature basis, now your equation gets reduced to root Es into cos this into phi 1 of t minus root Es into phi 2 of t. So this is of the form where you are combining, linearly combining your, so this should be the coordinate. Okay, the SI1 coordinate is this, and this is your Sij coordinate minus root Es into sin I minus 1 pi by 2 is the imaginary axis coordinate. Okay, so using these two, now we can define depending on what is the m value. Okay, we can define this to the m value. So this, it has to be I minus 1 2 pi by m. So that is first, and that is what missed here is 2 pi by m. So that value will come here, and when you map these coordinates onto the geometric space. For m equal to 4, you may get these points. For m equal to 8, you may get these points, 8 points, the coordinates of these points. Okay, so they are your ING, okay, the in-phase coordinate and the quadrature coordinate. Similarly, for 16, you will get your signal constellation like this. So in Emery PSK, you will see that all the signals are having equal amplitude. They are all on the circle. That means they are all having same amplitude. The frequency is also the same. The only thing they differ by is in their phase. Okay, so the phase is different for different signals. So the constellation is always going to be circular for the case of Emery PSK scheme. Okay. Now, how do you go about detecting the, and it's always two-dimensional only. You have the in-phase and the quadrature, or the phi 1 and the phi 2. So now when you have got your received signal, okay, so the received, you will get the received in-phase component and the received quadrature phase component you will be getting. So you have to estimate the angle, right? So what you can do, if you are doing a coherent detection, any angle variation caused by the channel that has been taken care of. So whatever is the angle of your in-phase component and quadrature component, so that your in-phase and quadrature, when you want to determine the phase shift, you can just do a tan inverse of y by x. The imaginary component assuming it is y, the in-phase component assuming it is x. When you do the tan inverse of y by x, that will give you what is the phase shift. Okay. So now in this signal, say I am getting an equivalent of root Es sine I minus 1 2 pi by m. That is what under ideal condition. So that is what I'll be getting as my imaginary component, and root Es cos I minus 1 2 pi by m is what I'll be getting as the real component when I do the detection. So if I do tan inverse of this by this, I'll be getting the angle. Okay. So whatever is the angle, that information I'll be able to extract. And that is what I want. Once I know this is the angle theta I, then I know what is the corresponding 4-bit to the log to the base 2 of n number of bit combination. Okay, so to do the decoding part. So the phase estimation, we can do it simply by taking the tan inverse of whatever is the imaginary component you got, or the phi 2 component you got, which corresponds to the imaginary component, and whatever is the component along phi 1 that you had got, you just take the tan inverse of that to estimate the angle. And you know all possible angles. This angle will not be exactly what you have transmitted, because noise that is got added, fading that is got added, they will change this y and x values. Okay, this y and x values would have got modified because of the channel noises and the channel fading and so on. Okay, so you may get some value theta which may not exactly be fitting into one of the possible thetas as per your modulation scheme. So what we need to do, we have to see this received theta or detected theta to which one it is close to. Suppose the theta which you estimated here lies close to this, then we will say that this theta, this theta to which it is lying close to, that is the transmitted phase. And once you have identified that, then you know corresponding to this what is the symbol bit combination that could have got transmitted. Okay, so that is how you do the decoding of your MPSK signal. So here again you can see the two steps. The first step is in identifying what is the in phase and the quadrature component received. And once you have the in phase and quadrature component, then you need to estimate the phase, for which you are doing the tan inverse of y by x. The quadrature phase by in phase received component, you take the tan inverse, you determine the angle, and that angle you try to see what is the closest angle, closest signal angle corresponding to your received angle, and based on that you make your detection. Okay, so that's the second part of your detection, or the baseband part of your detection. Okay. Now, probability of error for MAD-PSK scheme in an AWGN channel is going to be dependent on how much is this distance between the signals. Okay, so what is the distance you have between the closest signals? As I told you already, this is the minimum distance between closest signals. Okay, that is going to impact the probability of error, because if the distance is very less, the noise can easily take your signal. If you transmit this, the easily, because of noise, the signal may come closer to this one. Okay, so if the distance is less, it is more prone to noise and fading, and more probability of error would be there. But if the distance is more, you can make it less prone to noise and fading. So the distance plays a very important role, and so the probability of error, using the distance, is the distance between two adjacent symbols. So using that in the probability of error equation earlier shown you, which is dependent on DIK, which is the distance between the symbols, closest symbols, and N naught. So by substituting that, you can get an idea about what the probability of error would be. And that formula which I had given, that's basically an overestimate. It's a bound, actually, error bound. Okay, so we can get an idea about how much maximum the error could be when you're using this particular modulation scheme. The same thing when you do a non-coherent detection, without estimating the phase offsets, when you go about doing the detection, then what the error performance is. Okay, so they are given in terms of the based on the distance calculation. So you can also note that given obtaining your signal constellation also will help you. Once you have a signal constellation itself, you can now say what the maximum error you can expect from this modulation scheme. Okay, you can, because you can find out the minimum distance, and you will also have some idea about what is the noise level in your system, and using these two on the equation, upper bound the error equation, you can get an estimate of how much error you may have, and based on that it will be possible for you to identify whether you need to increase your ES value, okay, energy per symbol value or energy per bit value, so that you get the desired error performance. Application, based on the application, the error performance requirements may vary. So whether you are able to get the desired error performance for the particular modulation scheme. So that you'll be able to make an assessment. Okay. So some of the advantages here is that the bandwidth efficiency increases with n. but the drawback is that jitter or fading, any of the channel impairments which may have an impact on the face will definitely cause increase in the BER. So normally whenever NPSK signals are transmitted, the pilot symbols are also transmitted so that we can get some idea about what are the impairments that are happening in the, or get some idea about what's happening in the channel. Okay. Now coming to the QAM. So once you have some idea about how in general using basis you're able to map modulation, okay, then same argument holds good for any of the other modulation schemes. Okay, so now Emery-Quam, the signals are now, it's going to be combination of amplitude and phase. Okay, you are going to map m possible symbols as signals which will change in both amplitude and phase. In MPSK, there is no change in amplitude, there is only phase change corresponding to different symbols, phase shifts. Okay, whereas in MQAM, there could be amplitude change as well as phase change. It's a combination of amplitude and phase change, which is also reflected in this constellation, signal constellation of QAM, if you see. So as you can see that this signal is at a lower amplitude, whereas this signal is at a higher amplitude, this is at some intermediate amplitude and so on. Okay, so different signals are at different amplitude levels. Okay, so the equation for QAM is represented as root of 2e to ts. Root E min we are representing in terms of a minimum amplitude, okay, minimum energy signal. So square root of root E min into AI. AI is a scaling factor because you consider the least energy signal and all the other signals can be scaled versions, multiples, 2 times or 3 times or 4 times like that. There can be multiples of this minimum energy, okay, a minimum amplitude. So this AI represents a scaling factor and cost to percity, that is the basis. Root of 2 ts cost to percity is the basis, and this is a scaling factor along the in phase axis. This is the in phase axis. Along this axis, what is the scaling? And similarly, root even into bi is a scaling along the y-axis. Okay, and so based on this amplitude and this amplitude, the angle also will differ. Okay, so you have a certain amplitude here and a certain amplitude here. So if this is the signal point, then that will have a different phase compared to a signal with this amplitude and a signal with this amplitude. This is the point. So this phase will be different from this phase. So the two amplitudes will also indicate, okay, the in phase amplitude and the quadration amplitude you're going to get. That will also indicate what is the phase shift of your signal. So you can see that your signal model here is taking into consideration the amplitude changes as well as it is able to map the phase changes corresponding to the different n number of signals here. Okay, so I have shown more like a square kind of a constellation. It means you have equal number of points along this direction as well as this direction. Similarly, here you have 8 along this direction, 8 different amplitudes along the in-phase axis. Okay, but you can also have other kind of constellations, hexagon or any other kind of a symmetric pattern can be there. But the most popular are this kind of a square kind of a constellations, okay, for ML1. So here, of course, E-min represents the energy of signal with the lowest amplitude. AI, BI are independent integers relating to the location of the signal point. So essentially, as I mentioned, the scaling factors, which will map the, which will help you to identify the location of a signal point. T is the symbol period. And one thing to note here compared to Emery PSK is that the energy per symbol is not the same for all symbols. Some symbols have lower energy, some have higher energy. So the distance between adjacent symbols is also not constant, unlike Emery PSK, and hence the probability of correct symbol detection is also not going to be same for all symbols. Okay, and here again, since there is also phase variations happening here, the pilot tones would be necessary in order to correct for any phase offsets introduced by the channel. Okay, your received signal should reflect phase changes introduced by the symbol only, not because of the channel. So your pilot tones will help you to identify estimate channel and eliminate any phase offsets introduced by the channel. So the same phi 1 of t, phi 2 of t is used here also, and your modulation signal is this root E min into AI, that's the coordinate, in phase component into phi1 of t plus root emin into bi into phi2 of t, and root emin ai and root emin bi are the coordinates of the message point in the geometric space. And we can give this a scaling element. Considering a square constellation, we can tell what this ai and bi should be, what the scaling factor should be. Okay, so now we take the example of a 16 QAM. Okay, and so m is 16. So the L value is nothing but the square root of m. That tells you how many points are there along a particular axis, how many amplitudes are there along a particular axis. So which is nothing but square root of n, which is in general depicted as L. So L in this case is 4, and so for a square constellation of order 16, scaling factors are given like this. Okay, and this can be generalized to any m value using L. All this will get replaced by L here. Okay, and L minus 1, L minus 1 like that, it will get replaced here. And once you have this AI based scaling factors, now you can write your get the coordinates for your signal, or you can write down your signal. Say you want to write down the signal value S11, the first signal here. Okay, so this is represented with scaling factor of -3 and 3. So we can write -3 into root emin, because AI is going to be -3, BI is 3. So -3 into root emin into phi1 of t plus +3 into root emin into phi2 of t. So that would be your signal corresponding to this point. This will have amplitude corresponding to this and the phase corresponding to this point. So that is one signal. Okay. So likewise, every signal can be, so you can see an array here. It's a 4 cross 4 array. Similarly, this matrix is also 4 cross 4 matrix. So the you have a 1:1 mapping between this signal and this array element. And so using the respective array element, you will formulate the signal, okay, which needs to get transmitted. So here, because you are using the amplitudes are not constant, the envelope is not constant, you can use only linear devices like linear amplifiers, linear any device which you use has to be have a linear region of operation and so on. So that's how you generate your signal. So this is the generalized matrix for scaling matrix for the case of m equal to L square. So you can see the matrix is written in terms of, given in terms of m. So any order QAM, you can define your the scaling matrix and accordingly generate your modulation signals also. And of course, detection is, you will use the same detection methodology. You have your you will estimate, you are transmitting root emin into AI, comma root emin into BI, so the in phase and the quadrature phase that you are getting transmitted, but you will not exactly receive root emin into AI, because that will be, what you will receive is a noisy version of root emin into AI plus some noise. Similarly, on the quadrature channel, you will receive root emin into BI plus noise. Okay, so we have to see now in the signal constellation where this received vector will lie. So I say I'm transmitting this symbol and I'm getting a received signal which is actually lying here, because it's in phase coordinate, quadrature coordinate, both have been impacted by noise, added or subtracted by noise. So suppose I get I receive the point here, then I have to now find the I need to find out which is among all the 16 signal points, which point is closest to what I have received. So how I can do that? I need to compute the distance from this received point. I need to compute the distance to this one, this one, this one, this one, like that. I need to compute the distance with all the 16 signal points. Obviously, if my received signal is lying here, this point would be the closest. All the others would be much farther away from the signal point. So my receiver will make a decision that this is the signal that got transmitted, corresponding to which I have received some signal which is lying here. Okay, but if noise is very heavy, then the possibility is that I transmit this signal, but my received vector is lying here. Okay, if noise is very high. Okay, in which case what the receiver will do, the receiver will actually decode that this was the transmitted symbol. So now you can see the error. Your 0100 was actually transmitted, but what you have received is 0111. Okay, so 2 of the bits have been erroneously received. So over a period of time, when you count number of bits that have been received in error, that is what we call it as the error rate. Okay, number of bits in error by the total number of bits that got transmitted, that is your bit error rate. Okay, so in order to keep the error within desired limits, definitely your received signal should be closer to the received sector transmitted vector. In other words, it should be closer to this one, and depending on the noise level you expect in the system, what you may have to do is you have to place the signal points much farther or uh, closer. It should depend on, you can just expand, blow this square array, so that suppose you double all these amplitudes. Okay, so it will be a bloated 16 points, and in which case, if the noise is high also, still you will be correctly, that received vector will correctly fall in the region surrounding the desired signal vector. Okay, so bloating your array means that you are increasing your transmit signal power. Okay, or the energy, the root even energy which you're going to spend, you are going to increase. Thereby, your area becomes larger, and the energy per signal is also going to get increased, so that the noise is not going to have much of an, whatever level of noise you had may not have much of an effect. Okay, so that is how we can improve the bit rate performance. And before I wind up, I would like to just make a comparison between MPSK and NLFAM. So there are two important parameters which are useful in comparing different modulation schemes or any schemes for that matter. So one parameter is called as the bandwidth efficiency. Bandwidth efficiency tells about how effectively you are managing your available bandwidth. Okay. So with the available bandwidth, what is the maximum rate I am able to transmit? Okay. So this is defined in the unit of bits per second per hertz. So per hertz of available bandwidth or per usage of the channel, what is the maximum rate I can transmit? Okay. So this ratio is called as the bandwidth efficiency, and another important parameter is the power efficiency. So this is given, this power efficiency is defined in terms of the EB by N naught that is required, bit energy to noise ratio. Okay, so how much bit energy I require for a given level of noise, so that my receiver, at the receiver, I am able to have a certain level of desired level of PER. PER represents probability of error. We can also give this in terms of the bit error rate for a desired bit error rate. The desired bit error rate will change depending on the application. So for wireless, generally you can consider 10 power minus 5 or 10 power minus 6. So those kind of bit error rates can be considered. So to achieve a BER of 10 power minus 6, what should be the bit energy to the noise density? Okay, that should be available at the receiver input, so that I will get this BER, achieve this BER. So that value is called as the power efficiency. Power efficiency is usually used to compare two systems. Now, if one system I use is requiring a lesser EB by N naught, and the other system is requiring a larger EB by N naught, then I say the one that is requiring a lesser value of EB by N naught to get the same error performance is a efficient system, whereas the other system is requiring more energy to achieve the same error performance. So it is not power efficient. So using this EV not for desired bit error rate, we can compare different schemes or different modulation schemes or different coding schemes and so on, to see whether which of the schemes is more power efficient. Okay. So these two are very important parameters in comparing different modulation schemes or coding schemes and so on. So in MPSK, when you go for higher order MPSK, you can see that for QPSK, the spacing between the two symbols will be this much, but whereas for so this will be the spacing, okay, the minimum distance. But when you increase the number of points to 8, you see that the minimum distance is decreasing. Now, definitely, MPSK is going to be more prone to noise, error caused due to noise, because the spacing is now decreasing. So it will be able to sustain only lesser level of noise. Okay. So the only way to overcome this is, when you want to go for 8 PSK, you increase the size of the circle or the radius of the circle. That means you are now going to use a larger value of symbol energy. Okay, you have to increase your energy usage, so that now the spacing which you get is going to be similar to what you may have had in the case of a QPSK scheme. Okay, so that is how that's the way you can kind of improve your error performance by increasing your signal energy or increasing the minimum distance between the closest points in the signal constellation. Okay, so if you further increase the to 16 PSK, you can see that again the spacing is decreasing. Now you want to maintain the same error performance. Now you have to blow your circle further. Okay, so that the spacing between two neighboring points will should increase. So you see that as we go for higher and higher values of n, okay, you will notice that the energy requirement, the minimum EV not requirement, that is also going to keep on increasing. Okay, in the Emery PSK scheme. Same thing happens for NQAM also. As you go for higher and higher orders of Emery values, your the energy requirement will also keep on increasing as the M value increases. But when you compare these two, when you compare QPSK or Emery PSK with Emery QAM, you see that in Emery PSK, all the signal points are lying on a circle, and the distance between the closest points, you are getting some value here. Whereas in the Emery QAM, we are using multiple amplitudes are used here. As a result of this, you have a alternate way of arranging the 16 points in a two-dimensional space, okay, and that results in the minimum Euclidean distance between the neighboring closest points happens to, this could be slightly larger than what you see as the closest distance between any two points in an Emery PSK scheme. Okay, so this is in the way you have arranged your constellation using both phase and amplitude. Okay, so that gives rise to a direct benefit in terms of increasing this minimum Euclidean distance for NQAM compared to a Emery PSK scheme. So the daemon which you have for Emery PSK is less than the daemon for Emery QAM for the same value of n. And this also translates to the average energy. You also notice that the average energy of Emery PSK signals is same as the energy of all the signals, because all energy have equal signals here. Whereas the average energy realized in Emery QAM is much lesser, because signals, you have signals with lower energy and signals with moderate energy and signals with higher energy. If you put them in circles, put the signals in circle, you can see that there are signals with three different energy levels that are available here. So the average energy here is going to be much less compared to the average energy of Emery PSK schemes. Okay, so considering the distance is more, but the average energy consumption is reduced, okay, for the same value of n. So keeping all these points in mind, when you try to compare the bandwidth efficiency and the energy efficiency for MPSK and Emery QAM, so I have given this in the form of a table. As n value increases, you're able to see that the bandwidth efficiency is increasing, but the energy efficiency is decreasing because the EWA and not is requirement is increasing. Okay, increasing EWA and not means power efficiency is decreasing. Okay, so that's a trend you see for both MQAM and Emery PSK. But in terms of when you compare both of these, MPSK and MQAM, for say I have just highlighted the case of 16 here. Okay, 16 you have an bandwidth efficiency of 2, and you see that MQAM is also giving you the same bandwidth efficiency. So in terms of bandwidth efficiency, both are similar, but in terms of power efficiency, you see that Emery PSK requires 18.5 dB, whereas Emery QAM requires only 15 dB. So there is a 3.5 dB difference here. So this means that Emery QAM can give you same error performance with half the energy requirements as that of Emery PSK, less than half the energy requirement. 3 dB corresponds to half. Okay, so it's since there is a minus 3 dB change compared to MPSK, whatever is the power energy level required for MPSK, less than half that level is sufficient in Emery QAM to give you the same error performance. So that's the benefit of Emery QAM. So if you look into the standards, you will see that Emery PSK, you may go only up to a certain level. Beyond that, you will see that all the higher order Emery modulations are all quadrature M-QAM based. Okay, so all the 128 QAM, 126 QAM, as you go higher and higher, it's all quadrature amplitude modulation, because it's going to give you a significant benefit in terms of energy efficiency without compromising on the bandwidth efficiency as compared to MLPSK. Okay, so that's all I wanted to brief you about MLPSK and MLQAM here. And so these are all some ways of representing in a plot how with the reference to the Shannon's curve. This bandwidth efficiency, energy efficiency, they are all derived from the Shannon's information capacity equation. And so this is a limitation that is given by the equation, and you can see where your modulations are fitting in. All the circles indicate Emery PSK, and all the diamonds indicate Emery QAM. You can see that Emery QAM are energy efficient in the sense this axis represents the energy requirement, EBY not requirement, and this represents the efficiency, bandwidth efficiency. So bandwidth efficiency wise, if you take M equal to 16, they are the same, but energy requirement wise, you can see it is much efficient. QAM is much efficient. Same holds good for any higher order modulations also. Okay, so so we always need to trade off between bandwidth efficiency and power efficiency. Take these things into consideration in a particular system. And in practical systems, depending on the loss levels in a wireless system, loss level, and whatever is the EB naught that is available at the receiver, the M value would be adapted. Okay, so if the M or the energy available is much higher, then a higher value of M is being used so that you get a better data rate. When the energy received is EB not received is much lesser, then the M will be reduced so that you have connectivity, but your data rate gets reduced. Okay, so with this, I think I'll wind up the talk here. We are already exceeded time. Thank you very much. If you have any questions, you can just ask these questions. Any questions from the audience? Okay, there are no questions. I'll just thank you all.
Thank you, ma'am. Thank you for joining us.
Yeah.
It's wonderful to have you with us. Thank you, ma'am.
Thank you very much. So I take leave now. It's Dr. Shadi.
Yes, ma'am. Professor Mani, ma'am, can we start, ma'am? Sorry for making you wait.
No problem. Yeah.
Yes, ma'am. So good morning and welcome back to session 2 of the session on OFDM. To begin with, I would like to introduce the speaker of this session, Professor Venkata Mani V. Dr. V.V. Mani is a professor with the Department of Electronics and Communication Engineering, NIT Warangal. Ma'am has received her BE and ME degrees in Electronics and Communication Engineering from College of Engineering, Andhra University, and PhD in Electrical Engineering from Indian Institute of Technology, Delhi. Her area of research interests include wireless communication, signal processing for wireless communication, MIMO, OFDM, millimeter wave propagation and green communication, visible light communication, 5G new waveform design, software-defined radio, and testbed for 5G. She has numerous publications, 100 plus in credit in national and international conferences and journals. Ma'am is a fellow of Institute of Electronics and Telecommunication Engineers, India, and senior member of IEEE. Ma'am has completed many funded projects and has authored few books as well. We are happy to have you, ma'am. Thank you for joining us. Over to you, ma'am.
Yeah, thank you. So actually, I joined through 2 devices. Is it okay?
Yes, ma'am, it's okay, ma'am.
My voice is audible?
Yes, ma'am, it's audible, ma'am.
Okay, okay. I keep my camera off. Okay. So good morning to everyone. Is my screen visible? Just a minute.
Yes.
Yes, okay. So for me, today's given problem is the orthogonal frequency division multiplexing. I hope the many of the participants are already known about OFDM. And if you have any, is there any chart available? Yeah. So I'm observing the chat box as well. So if you have any doubts, please let me know with typing on the chat box, or we can through the voice as well. Okay. So orthogonal frequency division multiplexing is why it is important and for the wireless communication or a wired communication, and how it is evolved into the quasi communication as well, and what are the challenges and what are the challenges and problems issues with the OFDM. So we are going to learn all about orthogonal frequency division multiplexing. So I will be talking about OFDM, what is intersymbol interference, and what is the difference between frequency division multiplexing and orthogonal frequency division multiplexing. And we design a OFDM transmitter and the role of FFT and IFFT in OFDM, and as well a role of a cyclic prefix in OFDM, advantages and applications of OFDM, in between the evolution of OFDM, how it was started, right? So the introduction to OFDM, it is a modulation. Information is actually mapped onto the changes in the frequency, phase, or amplitude, and so this is also a kind of a multiplexing, which allows accommodation of users in the given bandwidth. So that means it is a combination of both modulation and multiplexing, right? So modulation and the multiplexing in the sense, so in this technique, the given resource is actually the bandwidth. So this bandwidth is shared among individual modulated data sources. So now we know normal modulation techniques like AM, PM, FM, BPSK, QPSK. These are all single carrier modulation techniques. So where the incoming information is modulated over a single carrier. But whereas OFDM is a multi-carrier modulation technique, which employs, it has several carriers within the allocated bandwidth, and they convey the information from source to the destination. So now each carrier will employ one of the several, any modulation technique. You can take BPSK, QPSK, QAM, etc. So this orthogonal frequency division multiplexing is one of the special case of multi-carrier modulation scheme. So if you look at the diagram, the one diagram has a tap and another diagram is a facet, which is showing the water in two different ways. One is through tap, the whole water is coming out at one time, and through the shower it is coming through the streams, right? So these are, that means these are modulated by different carriers and they are orthogonal to one to one. So first one is the diagram is regular single carrier frequency modulation scheme, and the B is OFDM, orthogonal frequency division multiplexing format. So before understanding the OFDM modulation scheme, so we will see some mathematics hidden behind. So how this scenario is to be narrated, and what are the problems in OFDM scheme, right? So before going to that, maybe I'll use my OneNote to right. So let's take a basic principle of OFDM. So we have a single carrier. Maybe I take more time. So centered at center frequency of C, and it has the bandwidth of B, right? So this is the single carrier system. So now the time and the bandwidth, as we know, they are inversely proportional. So in this case, if the bandwidth is 10 megahertz, we know that this is the broadband system. If you take broadband system, so if the bandwidth is 10 megahertz, the time will be 1 by 10 megahertz. That means 0.1 microseconds. Okay, so this 0.1 microsecond is, I can use it for the symbol time. And you know, the wireless channel model, the delay spread, the TD is the delay spread, is the major concern for our systems. So this delay spread of, that means till how much time your signal is still present in the channel, conveyed by delay spread. So this delay spread of the channel is important. Generally this delay spread, suppose if it is between 2 to 3 microseconds, then the symbol time you can make the symbol time T is, in this case it is 0.1 microseconds, and T is much less than the delay spread. Okay, so that means the problem of inter-symbol interference, when the symbol time is much less than the delay spread, we can eliminate this inter-symbol interference. I'm not talking about all inter-symbol interference derivations and all, but this is a general scenario. So in broadband systems, wireless systems, when this symbol time, so as the T, suppose if you are increasing from 10 megahertz to 100 megahertz, let's take one example. So if it is 100 megahertz, then the bandwidth is going to decrease, right? So that means 1 by 100 into 10 to the power of 6. So that means 0.01 microseconds, right? So this 0.01 microsecond is the sorry, 0.01 by is the time, the symbol time. So earlier the symbol time was 0.1 microseconds. Now if you increase the bandwidth, it is becoming 0.01 microseconds, right? So this time is much less than your design delay spread. So this to overcome this kind of an inter-symbol interference. So the next proposal was to overcome this ISI. The next proposal was, so use the bandwidth given and divide this bandwidth. Suppose it is B equal to 100 megahertz. Then divide this bandwidth into subbands. Divide this bandwidth into subbands. Okay. So these subbands, that means each band will become the band divided by, suppose if you are dividing into n subbands, then your bandwidth of the subband is B by n, right? So if it is B by n, suppose in this example, if you take n equal to 1000, then your bandwidth, earlier bandwidth, if you take it as 10 megahertz, then your B by n factor will become, so 10 into 10 power 6 by 100 by 1000 will make you 10 kilohertz. So the bandwidth of the system is now only 10 kilohertz, right? So this 10 kilohertz bandwidth, now if you consider this bandwidth, what is the symbol time in this duration? So the T will be 1 by B by N, that is computed earlier. That means it is now 100 microseconds. So the symbol time now has become 100 microseconds, and whereas your time delay or delay spread is approximately 2 microseconds, then your T, in this case the symbol time, is much greater than the delay spread of the channel. So the new symbol time is much greater than delay spread of the channel. If this is the case, we can avoid no inter-symbol interference in new system with multiple subbands and subcarriers in each band. So n subcarriers, such a system with multiple subbands and multiple subcarriers, this is called multi-carrier communication, multi-carrier modulated signal, right? So MCM system, also called as MCM system. So this MCM system is the basis for OFDM, orthogonal frequency division multiplexing. Now, so the transmission in these multi-carrier systems is divided into n subbands, and we look at this at a center frequency. Let's take this the center frequency, and it is allowed with the bandwidth of b by n. Then that kind of a system is called a multi-carrier system, and the center frequency maybe we'll treat it as f0, center frequency 2f0, and minus f0, minus 2f0, so on and so forth. So there are total n number of subcarriers. Suppose any kth subcarrier I want to see in this system, the kth subcarrier value means k times f0. So this k times f0 is nothing but k times, what is the center frequency? Bandwidth by n, right? So the bandwidth is divided by n number of subcarriers. So the kth subcarrier frequency will take it as k times b by n. So this kth subcarrier is actually e power j 2 pi k times that f0. So this is the subcarrier frequency in exponential form. Then what is the transmitted signal? So transmitted signal we can write as xk in its nth carrier subcarrier, that means the kth symbol. So we transmit a symbol in this band, that is kth band. That symbol is denoted by xk. So what is the transmitted signal actually? So that means the actual transmitted signal, we will write it as sk of t is xk is multiplied with this subcarrier. That means 2 pi k f0 into t is your signal format. So the signal transmitted on the kth subcarrier. So this is on the kth subcarrier. Okay, so this subcarrier, that is the multi-carrier modulation scheme, modulated such how many subcarriers? There are n number of subcarriers. So the transmitted signal y of t, we can write it as summation over k of sk of t's. That means we will write as summation over k xk e power j 2 pi k f0 into t. This is your sum of the all transmitted signals across all n subcarriers. Okay, and k may be running from 0 to capital N minus 1 subcarriers. So this received this signal. Suppose we ignore the noise for time being. The received signal is generally we write R of t as y of t plus noise, additive white Gaussian noise, n of t, add the channel noise I'm not including. So now for the time being we remove the noise. So the received signal is y of t. Then, so this looks like similar to a Fourier series. So the Fourier series representation, the symbol k equal to 0 to n minus 1 xk power j 2 pi k f0 of t looks like a Fourier series representation of the signal. Now from this signal, received signal y of t, I want to extract one xl, lth symbol. Okay, so that is ported onto lth carrier. To extract this symbol x of l, so generally what we do on to extract this symbol, we pass through a matched filter or a correlation receiver, right? So what the correlation receiver does, the receiver signal is multiplied by the corresponding filter response. So here in our case, the filter is e power, that means e power minus j 2 pi l times f0 of t. We multiply with that and we integrate, right? So that means to extract my x of lth symbol, what we do perform the operation over that symbol period e power minus j 2 pi L f naught into t on y of t dt. We do this integration. Okay. So when you do this integration, we can exchange. That means y of t is a summation value. So I can write x of L as f naught summation over k x k and integration between 1 by f naught e power minus j 2 pi L f naught t into e power j 2 pi k k f naught into t dt. So this is my operation. So what we are doing? We are doing the inverse operation to receive, to extract by XLH symbol, right? So when you do this XLH symbol, so this integral is actually, we can write this whole integral as e power j 2 pi k minus L into f naught times t of from 0 to 1 by over that symbol period dt, right? So we know very well. So this extraction of this signal e power j 2 pi k minus L f naught of t will tends to a delta function of this integration if k equal to L. If k not equal to L, if k equal to L, it turns out the integration will become 1 with a delta function. If k not equal to L, it is becoming 0. That means this is a sinusoid with fundamental period, and the integrating over that fundamental period of 1 by f naught, so the sinusoid will become reduces to a DC signal. So the value of the signal becomes summation over k x k delta of k minus L, right? So at the receiver, so we did a coherent demodulation with e power minus j 2 pi L f naught of t to extract my XL, right? So to extract my XL. So by, this is anyway k when k equal to L. So at the receiver, so by correlating with e power j 2 pi f naught of t or any matched filtering with this formula, we can extract the LH symbol. So this is the basic principle of when k equal to L, the delta function becomes 1, and at k not equivalent to L, the delta function becomes 0. Then I can extract f naught XL, right? So if the same value, if it is multiplied, otherwise it is coming to 0. So this is my received signal. So we could able to receive my X of L. So we can extract the LH subcarrier. So that is basic principle of a multi-carrier communication system. So earlier we have a bigger bandwidth, right? So in this bigger bandwidth on the time axis, we used to send the t equal to 1 by tb is the bandwidth available. On the time scale, we are sending so the signals. Now the total bandwidth is divided by n times b, and so this is the whole bandwidth. Now this whole bandwidth is now divided into n times b parallel streams. So, and in each stream we are multiplying with an orthonormal carrier. Now this bandwidth becomes n by b, and this is called a multi-carrier communication system, MCM system, modulation scheme system. And so we send n symbols across n subcarriers. So like that. Okay. So this is the principle of multi-carrier communication. Okay. Now we'll go back to the presentation. So what is single carrier and what is multi-carrier is presented. Now, so anyway, so mitigate the frequency selective fading and all I told about intersymbol interference. This OFDM actually mitigates the problem by converting the entire frequency of the selective fading channel into a small flat fading channels. So that we have seen from the diagram, because the total bandwidth available is suppose 100 megahertz. We divide it into 10 megahertz each with n equal to some 1000 subcarriers. When the bandwidth is reduced, definitely the symbol timing is going to increase. So when the symbol timing is increased, the frequency selective fading channel has become a flat fading channel by individual subcarriers. So this flat fading is easier to combat when compared to the frequency selective fading by employing some simple error correction and equalization schemes. So I'm not going deep into this multipath projection. So now right. So so how our problem, that is when you are sending your signals over a frequency division multiplexing system to an orthogonal frequency division multiplexing system. So the problem of actually a frequency selective fading is solved when data is transmitted in parallel, like a big truck is taking a lot of load for the shipment, but what we are doing, we are divided this load into a smaller trucks and we are sending over the smaller bandwidth intervals. That means the symbol time is increased. So when the symbol time is increased, the frequency selective nature is converted into a flat fading system, and also the inter-symbol interference is reduced. Are there any doubts? Okay. Now we'll go back and see some more expressions for how to generate the signal of the total subcarriers of capital N is difficult because large number of subcarriers. Okay. So to generate this kind of a signal, let us take, I have a bandwidth available for my system. So for this bandwidth, the given bandwidth, there is a maximum frequency and also a minimum frequency. So F minimum frequency. So maximum frequency, I'll take it as B by 2 and minus B by 2 in the available bandwidth. Okay. So in this available bandwidth, since the signal is band limited and the maximum frequency of maximum, if you are considering it as B by 2, then to sample the signal using a Nyquist rate, we need 2 times of that maximum frequency. That means 2 times B by 2. That is capital B is your sampling frequency required is B. So my sampling interval, if you write, is 1 by sampling frequency. I'm not writing the full. So 1 by sampling frequency, 1 by B, that means the T, capital T. So what is the LH sampling instant? Suppose if you take LH sampling instant will become L into T. That means L by B. This is my LH sampling instance. Okay. So your transmitted signal earlier also I wrote y of t as sum over k. We are transmitting over n or n basis functions. That means different carrier frequencies 2 pi k times f naught into t. This is the way we are transmitting. So from this signal, I want to extract XL. Okay. So to extract XL, so RYL, to extract YL, I translate T into L times capital T. Then this becomes K, XK, e power j 2 pi K, F naught, T is translated into L into capital T. Right? So that means what is happening over here? Sum over K, XK, e power j 2 pi K, F naught L by B, right? So what is that? This summation is becoming xk e power j 2 pi k fundamental frequency. What is the fundamental frequency we allocated? So the total bandwidth is divided by n number of subcarriers. That is my frequency used, right? So that means it is B by n times L by B. So what is happening over here? So B gets cancelled. I have a signal K, xk, e power j 2 pi k L by capital N, right? So if you look at the signal to extract an LH subcarrier signal, so we did the sampling, and upon sampling, so we have seen that the transmitted signal, to look at the LH sampled signal, we did the sampling of the signal y of t, and that y of t at the LH instant is becoming xk e power j 2 pi kl by n. So this kind of a format is similar to your IFFT oblique FFT format, if you remember. So FFT is Fourier transform, IFFT is the inverse Fourier transform. So in our case, it is becoming e power j 2 pi kl by capital N. It is in the positive side. So that means we treat this signal as inverse Fourier transform signal, right? So R inverse discrete Fourier transform signal. So this YL is, that means LH inverse discrete Fourier transform point of what? Of your transmitted symbols x0, x1, we go up to onto the nth subcarriers. We are transmitting n symbols x0, x1 of x of n minus 1 is given. So then the LH IDFT point is computed. So the whole multi-carrier communication system in this case looks like, so we can implement very easily this expression using FFTs and IFTs. Okay, so x0 and x1 are your transmitted symbols, transmit symbols, and so on to the nth subcarriers. And so n point IFFT, if you compute, we are receiving y of 0, y of 1 up to y of n minus 1. The small case I am writing for n point IFFT. So if you compute FFT onto the transmitted symbols, we can retrieve your transmitted samples, that is y0, y1, y of n minus 1. This is called a sampled version of multi-carrier modulation system. Okay, so now we transmit this signal over the channel. Anyway, it is present. So y, x is given, is translated into the, that means your symbols after computation of your IFFT, after computation of your IFFT to the IFFT x case are given, then IFFT gives x, then it is passed through the channel, we receive the signal and do the reception FFT. Okay, so when it is passed through the channel, it becomes x plus n, additive white Gaussian noise. For the time being, just I am ignoring additive white Gaussian noise to retrieve my signal. So again we take n point FFT at the receiver. So FFT and IFFT are the key principles for OFDM, orthogonal frequency division multiplexing, right? So we'll go back to the presentation and see what is happening. So earlier, using a single carrier, we transmitted the signal. Now using multi-carriers, we are transmitting the signal by dividing each by n times. So the bandwidth is becoming less, the symbol time is becoming more, and we could eliminate the inter-symbol interference because the t is much greater than the delay spread of the channel. If t is much less than the delay spread of the channel, we cannot eliminate inter-symbol interference, right? So now look at the orthogonality means. What is the orthogonal frequencies? So the peak of the each signal, look at the peak of the each signal is, this is the peak, these are the peaks. The peak of the each signal is Just a minute. Okay. So the peak of the each signal coincides with the trough of the other signals. So when one signal is going to the maximum, the rest of the signals are passing through a zero axis. Okay. So that means when they are summed up, that means they look like the F1, F2, F3, F4 signals are orthogonal to 1 to 1. Right. So now, what is the difference between frequency division multiplexing? We have used earlier also. So we divide the band, and on each band we use to transmit the signals. So what is the difference between frequency division multiplexing and orthogonal frequency division multiplexing? So in FDM, so entire channel bandwidth, if we take, we divide it into subbands. So how we divide it into subbands? Suppose I have an entire band and we divide it into subbands, and also in between the subbands we keep some guard bands. This is called guard band and this is a subband, and again subband and there is a guard band. So guard band, subband and guard band, like that. So this guard band is taking some amount of bandwidth, and subband is having a defined bandwidth. So guard band is eating some amount of the bandwidth of your bandwidth of your communication system, right? So that is the difference. That means divide it into subbands, and to prevent the signal from one band not to be overlapped with the signals of the other subband, we provided some suitable amount of guard band is left between each subbands. But this guard band actually is also an inefficient way of usage of the bandwidth. So that is shown in the figure. So that means now, but if you look at OFDM, if you look at the OFDM, the bands are overlapped on 1 to 1. So F1 is a frequency of one band, F2 is another one, F3 is F3, F4 and so on and so forth. But they look like overlapped on 1 to 1, and we have not provided any guard interval. But only the criteria what we have conditioned on it, when one signal goes to the peak, the other signals are going to the troughs. That's the difference between OFDM and FDM, right? So, what is the advantage to when you are making like this OFDM to FDM? So, the bandwidth requirement of OFDM and FDM, if you see, earlier we have divided into channels and also provided in with subbands. Now, because of the overlapped subcarriers, we are saving this much amount of bandwidth. So, we are saving this amount of bandwidth, right? So, this much amount of bandwidth saving is also possible. So look at some of the historical development of OFDM from multi-carrier to orthogonal frequency subbands. So anyway, these are the colored figures. The N subcarriers are placed with different colors for visualization purpose. So earlier frequency division multiplexing subcarriers are separated by a frequency guard bands from pink, yellow to blue. But whereas the same case, pink, blue, pink and yellow, they are overlapped if you look at, and only one peak is when going to one peak, the other signals are going to the troughs, right? So now see the development of OFDM. So this development of the OFDM in 1966, US patent application launched on orthogonal frequency multiplexing data transmission system, 1966 itself. In 1969, the use of DFT for OFDM was released, and in 1980, so that means after a 10 years gap, use of a cyclic extension, cyclic prefix is introduced, and later in 1985, so it is used for the mobile communication. SIMNI is used the OFDM for mobile communication. And in 1987, Lasley and Allard also used OFDM for broadcast. And in 1990, OFDM, DMT for digital subcarrier loops, and 1995, capacity of MIMO systems is computed, and in 2001 is also introduced OFDM for optical wireless. In 2008 and 2005, OFDM for optical fiber communication, and so on and so forth. So the progression of the OFDM system since the invention in the year 1966 till today 2025, the progress is going on, and still we are in 5G communications also. It is proposed to use the OFDM because of the simplicity of construction, and that is detection and demodulation, construction and the demodulation techniques. Okay, so now the design of OFDM transmitter, the physical OFDM transmitter, how do you do? So we consider the data bits used in OFDM, suppose they are D0, D1, D2. Okay. So now, while firstly what we do, the design of the OFDM transmitter, we'll consider n number of subcarriers. So as a generic case, we have n subcarriers. Each subcarrier is centered at frequencies, and those frequencies are orthogonal to each other. Usually multiples of subcarriers. So orthogonality principle, if you know very well, that means suppose if I am designing cos 2 pi f1 of t, and another frequency is cos 2 pi f2 of t, and these two are orthogonal. To say these two are orthogonal, what we do? We multiply cos 2 pi f1 of t and cos 2 pi f2 of t, dt integration must be equal to 0, such that we have to maintain the delta difference, delta frequency, how much delta frequency we have to maintain between these two. We have to derive the equations and place such frequencies into the orthonormal basis functions. Okay, so that means first we have to find the each subcarrier frequency centered at some frequency. The second design parameter is the modulation format. What we wish to do, we can OFDM signal can be from any of the form, any of the modulation scheme you can take, BPSK, QPSK, or QAM. So BPSK means 1 bit at a time, QPSK means 2 bit at a time. The QAM depends upon how many number of bits you want to translate. So your original data, so coming D0, D1, D2 is modulated onto a BPSK, QPSK format, and then passing through your n orthogonal subcarriers. Okay, so the first data is to be converted from serial stream to parallel stream. So the data bits D0, D1, D2, D3, D3, so on and so forth are coming. Then we have to modulate. Let us take this D0, D1, D2 are of from BPSK, binary phase shift keying modulation scheme. Suppose I want to implement for OFDM scheme. Then what I do, each data bit I will port it on to my n orthonormal basis functions. So let's take one example, n equal to 4 basis functions. That means 4 carriers we will take. So these first take this data stream and make it into a parallel form. So D0, D1, D2, D3, place them in the parallel form and send each one onto one orthonormal basis function. Each one onto one orthonormal basis function. That means F1, F2, F3, F4, right? So take the output and give it to the summation. Give it to the summer. This is your I of t signal. That's what we are supposed to do, right? So now, we'll see. So convert the data into a parallel bit stream and modulate onto this. So can be looked into this format. So D0, D1, D of n minus 1 serial to parallel. So after converting into them into the parallel, the constellation mapper takes BPSK, QPSK, or QAM, and so according to the QAM constellation, so So that means that symbols S0, S1, S of n minus 1 are modulated onto here in this diagram. Sine carrier frequencies are taken F0, F1, F of n minus 1, and such signals are passed through, summed up and passed through, treated as a OFDM signal. So now look at the original diagram. So the following example actually illustrates the OFDM transmission with BPSK modulation. So if you look at the diagram, the data bits are 10, 10, 11 and so on and so forth. In time T0, 10, 101. So D0, D1, D2, D3, D4. And so in this example, it is taken n orthonormal basis functions, n equal to 5. So in the next interval, another 5 bits, next interval, another 5 bits, next interval, another 5 bits. So in each timing interval of T0, we translate into symbols. So that means 0 is translated into -1, 1 is translated into 1. So that is called BPSK mapping. And we multiply this mapping by orthogonal carrier frequencies. That means in T0, I send 1 multiplied by sine, -1 multiplied by sine F1, 1 multiplied by F2, -1 is multiplied by F3, 1 is multiplied by F4, right? That is one OFDM symbol, the first OFDM symbol. The next stream comes in, again we take 5 bits, we multiply with the corresponding F0 to Fn, then that is the second OFDM symbol. So on and so forth, we transmit the symbols. Now, so the second example illustrates the OFDM transmission with the QPSK modulation scheme. So here the OFDM subcarriers are assumed as same for 5 subcarriers. So QPSK scheme, then what we do, we take 2 timing intervals T0 and T1. So we make them into parallel and we combine, because it is a QPSK, that means 2 bits at a time. So we translate that T0, T1 timing interval data into a complex nature. So suppose 1, 1, then 1, 0, 0, 1, all possible combinations we take, and accordingly, so -1 and T1 interval is translated into -j. So like that we transmit the signals. So in this one, T1 plus delta and 3 triple set. So only in 2 streams, 2 OFDM symbols are converted. Earlier 4 OFDM symbols, now only 2 OFDM symbols, because each OFDM has 2 bits again inside. They are multiplied by a single carrier. Okay. So this is the way we transmit a OFDM symbol. So any doubts till now? Maybe you can view your hand rise or message. Okay. So no problem. Then, so this is a translation. Then the role of FFT and IFFT in OFDM. So OFDM architecture we studied and described how to generate the basis functions, sinusoidal basis functions. So this sinusoidal, any one OFDM signal I have given with a different notation in the presentations. Okay, so this S of t in this equation, Sn of t, S sine 2 pi Fn of t, and that S of t symbols mapped to the chosen constellation diagram, and F is your orthogonal, F of n is represents the orthogonal carrier frequency symbols. So this equation is nothing but your IFFT process, inverse fast Fourier transform. So this breaks the signal into different frequency bands by multiplying the signal with series of sinusoids. So essentially this translates the signal from time domain to a frequency domain, right? So but we always view IFFT as a conversion process from frequency domain to time domain. So if you remember, the FFT is represented by these 2 equations. That means sine plus cos format, x of k, x of n, x of n. and its dual is represented by with x of k minus x of k cos. So IFFT is x of n, that is my original transmitted symbol. So for transmission of the modulation scheme, we use IFFT because it is exactly matching. X of k's we treat it as data symbols. There is no meaning if you take it is a frequency domain or it is in a time domain. So we treat them if they are in the frequency domain. So finally the transmitted signal, we by using IFFT, we modulate them onto the orthonormal basis functions of sine and cos with the different frequencies of k by n, and we treat that one as an IFFT process. For receiving system, we use FFT. Okay. So then IFFT and FFT are actually, they are dual and behave the behavior wise they look similar, only the sign symbol is different. So we can interchange the IFFT and FFT blocks, and since OFDM the final transmitted signal is to be in time domain, so IFFT is a more appropriate choice to use in the transmitter, which can be thought of as converting the frequency domain samples into time domain samples. Okay. So now the following figure, if you look at this figure, so IFFT in the transmitter eliminates the need for separate sinusoidal converters. Look at, so original transmission of a signal is nothing but multiplication by different sinusoidal signals, right? So the multiplication of the sinusoidal signals on the right hand side are replaced by an IFFT block. So to the IFFT, we are giving S0 to S of n minus 1 symbols. So they are actually coming from the constellation diagram of a BPSK or QPSK. Then it formulates into a OFDM symbol. Then, so both transmitter and receiver. So if you use IFFT at the transmitter passing through the channel, the received signal is passed through the FFT block, and we do the reverse engineering like demapper. So we the constellation diagram. So if it is a BPSK, we demap into the BPSK format and we extract the data symbols. That is D0 of your data bits, D0 to D of n. So those are all in parallel form. Again, we convert them into the serial form. Okay? So this is the process of FFT and IFFT. Okay. So the full structure of FFT and IFFT block is given in this diagram. I hope this is visible. And now we consider the role of cyclic prefix in OFDM systems, right? So let us take an ideal channel. A non-ideal channel is not a delta channel. That means H of t is not delta of t. That causes some delay dispersion. So this delay dispersion actually, let's take one example of how the cyclic prefix will make your interference less in OFDM systems. So cyclic prefix in OFDM systems, how do you write? Right? So we consider in one frequency selective channel. So my nth output after passing through the channel, how do you arrive at nth output? H of 0 times x of n plus h of 1 times x of n minus 1 plus h of 2 times x of n minus 2 and so on and so forth. Suppose the channel length is L, then we consider h of L minus 1 times x of n minus L plus 1 without noise. I'm not adding any noise. That means suppose x of n is transmitted, right? We receive y of n through the channel. That means given x of n and my channel response is h of t, a discrete channel if I take, output is y of n, eliminating the noise. That means my h of x of n x, and it is convolved with h of n, right, in discrete form if you write. So that convolution is nothing but the present sample of your system coming out of your system from the channel is multiplied with the first version of the channel, and h of 1, the next impulse, is multiplied by the previous version of the channel. Suppose, because it is a multi-path channel, right? So from so many paths we are receiving. Each path has its own weight. H of 0, H of 1, H of L minus 1 paths. Through these paths, the system is receiving my signal. So what was transmitted? The transmitted signal for the time being, if I consider x of n. So this x of n going through the h of 0, right? By the time, the second symbol is, because in a given time, my x of n is coming through this channel. Then the previous samples which are present in the channel are multiplied with their respective weights of my channel. That's the expression given here, without any noise, for a frequency selective channel. Okay, so the first set of symbols, when it is loaded onto the subcarriers, that means I'll write with first set with the curl. So x0 is the first set, x1 is so on so forth onto xn minus 1 symbols. These are the symbols loaded on n subcarriers. Okay. So then what we do? We compute IFFT of this. So when you compute IFFT, correspondingly I can write x curl of 0, x curl of 1, so on and so forth, x curl of n minus 1 are your samples. Okay. So in the first OFDM symbol is transmitted. In the second OFDM, so next we send a second OFDM symbol, right? Second OFDM symbol if you transmit, then just to differentiate between the first and second, I write without any curl x0, x1, x of n minus 1. So if you apply IFFT onto this second OFDM symbol, then this becomes x0, x1, x of n minus 1 after computation of the IFFT, right? So now consider these two consecutive symbols. Now, if you consider these two consecutive symbols, the first symbol when I am transmitted, x, so if I am writing together, so the first symbol is with the curl if we are writing x1 up to x of n minus 1 conjugate, and x0, x1 up to x of n minus 1. These two OFDM symbols, if you write consecutively, then if you compute IFFT symbol on one symbol and then later another symbol, my received system, that means after computation of IFFT block, this becomes x of 1, so forth, x curl of n minus 1, and x of 0, x of 1, x of n minus 1. Supposed to be like this. Okay. So now these symbols, actually we are transmitting these onto the channel, right? So consequently I am computing IFFT symbol by symbol, and we are transmitting onto the channel. So what is happening when you are transmitting onto the channel? The output for, suppose if I am writing, what is the output for x0, right? So x0 output, that means y0. What is my y0 output? My y0 output, if I am looking at y0 output, the channel weight multiplied by x0 plus what was my previous symbol on the channels, that is through the multipath it is coming, the channel weight multiplied by x curl of n minus 1, right? So plus h2 x curl of n minus 2 and so on so forth. If it is channel has a length of L, that means h of L minus 1 x curl of n minus L plus 1 is the output. The actual output is x0, h0. But what we are receiving? We are receiving the previous the previous IFFT computed symbols are also coming and placed on to your Y0. Okay. So this is also called interblock interference, IBI, interblock interference. So we have to avoid this interblock interference. So what you are supposed to do, that means when I am making the first symbol x0 to receive, I must receive only h0 x0. But I am also added with h1 and the previous symbol, h2, the previous symbols, and so on and so forth till the length of the channel is present in the channel. Okay, so we have to avoid such all these values to receive only x0, h0, right, over this L number of samples. So that means we prefix some L bar samples from that tail, or suppose you take the total length of one block, we take n plus some L bar samples of one block. So what we do, the cycling from the last OFDM block and then put at those values at the front of the OFDM sample. So that means, look at, I am adding L bar samples to avoid interblock interference, right? So to avoid interblock interference, we are placing these L bar samples at the front of your OFDM. So these L bar samples and original samples and the last L bar samples we are placed at the front of your OFDM block to avoid intersymbol interference. Why to avoid the why to avoid this interblock interference and intersymbol interference? Because we have seen when you are making out x0, we are also receiving the other block, other symbols information, right? That is present. That means in your original block itself, the last portion of your information is placed onto the first. When I receive the consequent blocks of my OFDM symbol, every LF bar is only the replica of the previous block. So I don't use this one for my detection scheme, I need not. So only I depend upon this, the length of my block. That is the advantage. So that means if you write x of n minus L bar, x of n minus L bar plus 1, like that, if you write x of n minus 2, x of n minus 1, then x of 0, x of 1, so on, so forth, x of n minus 1. Okay. So if you are making your block, that means your data symbols are in this fashion after computation of your IFFT. So after computation of IFFT, I am making x0 to x of n minus 1. But what you are doing, out of this x0 to x of n minus 1, n samples of this x0 to x of n minus 1 are placed at front of the information. So how many are placed? L samples are placed prior to the samples of your after computation of your IFFT. From the same samples are placed at the front. So now the interference is restricted to only one block. So there is no interblock interference, because when you receive x0, I'm also receiving the previous version, right? So this previous version is not important to me. So just you remove the cyclic prefix from the received signal. We try to decode from only X0 instance. So this makes, so interference is now restricted. So the response, if you look at the response of this X0, right, at RF1, if you write the response of X of 1, then Y1 if you write, Y1 is H0 times X1 plus H1 times X0 back. I'm going in this direction. H0 times X1, H1 times X0 plus H2 times X of n minus 1, X of capital N minus 1, and so on so forth. So we'll receive the symbols. Okay. Now we'll remove the previous versions. So we'll see the presentation, how it is presented. So now consider, we have considered. So we came to know that after adding cyclic prefix to each OFDM symbol, it mitigates the problem of ISI and interblock IBI by removing altogether. Okay. So look at the same example what I have written in the OneNote is also represented in this case. So now the symbol energy is spread across n plus ncp bits. So we are using useful data bits are n, and we are making a cyclic prefix of ncp bits having a length from 1 to ncp. So x0, x1, x2, x of n minus ncp, like that we go up to x of n minus 1. Then we are making a bigger size of your OFDM block. So the size of the OFDM block after computation of IFFT, we are adding the last NCP samples at the front. That means x of minus NCP to x of minus 1. So these NCP bits are copied onto the front, right? So after adding cyclic prefix, how it looks like a block diagram of a OFDM after adding a cyclic prefix. So from IFFT, we have generated x of 0 to x of n minus 1. And also we have added a cyclic prefix NCP data bits. Those are coming out of your IFFT block only. Okay. So that your parallel to serial values are now increased. Earlier n, now n plus NCP is the length of your data transmission. Now we have to convert them into serial format and send it as a OFDM signal, and again make serial to parallel. And now the extra redundant bits what we have added at the front of your OFDM symbol are to be removed before giving them to the FFT block. Okay. So we delete the cyclic prefix and give it to the IFFT and do some equalization and the constellation diagram demapper, and again make it to the parallel to serial computation. So these key ideas behind adding cyclic prefix is also we can look in a different perspective as what we are doing. Actually, we are converting a linear convolution into a circular convolution, right? So actually this kind of a linear to circular convolution makes the process of detecting the received signal by using a single tap equalizer. And also it is helping out to combat the problems of intersymbol interference and interblock interference. That's what I explained through my OneNote. No. So we have seen the historical background of OFDM when it was started, with the first patent, and how it is evolved into the broadcast systems. Okay. So there are many advantages, some advantages of OFDM, because it permits a densely packed and oversampling subcarriers, right? They are oversampling because they look like overlapped on one carrier onto the other. So overlapping of the subcarriers. So the spectral efficiency of the transmission scheme is more, and also the OFDM can be digitally implemented using FFT and IFFT algorithms, and it permits also the flexible use of the spectrum. And OFDM also supports different modulation schemes based on channel conditions, and also almost completely avoids need for an equalizer. Using a single tap equalizer, I can decode my signals. So this is used in digital audio broadcasting, digital television, digital televisions, wireless LAN, IEEE 802.11a, IEEE 802.11g, IEEE 802.11n, and 11AC, 11AD. And also it is used in WiMAX, worldwide interoperability for microwave access, and it is currently used in LTE and LTE advanced 4G mobile phone standards as well as in 5G. So I can show one paper. Okay, so a very good tutorial on orthogonal frequency division multiplexing. This is an intuitive guide to principles of communication. OFDM is explained in a neat manner using this paper. You can read multi-carrier frequency division modulation and demodulation, and how the bandwidth saving is happening. Okay, how the data stream is converted into a bit stream is modulated using a 4-carrier OFDM format, and how the bits are translated, and the diagram of the one on subcarrier 1 the bit is modulated, and how in subcarrier 2 the bit modulation, what is the waveform we are generating. So symbol 1 takes carrier in this diagram, symbol 1 takes carrier, symbol 1 takes carrier 1, symbol 2 takes carrier 1, they are all summed up. So when they are summed up, a OFDM signal in time domain and frequency domain. So in frequency domain, the frequencies are varying. In time domain, the sine waveform and cos waveform are changing, depends upon the bit nature. And so the parallel to serial bit stream. So one OFDM generated signal, how much it varies compared to the underlying constant subcarriers. Values are also mentioned with the need diagrams. Okay, so when you compute the IFFT and IFFT, what is the output of those FFTs and IFFTs is also given in this paper. And because of the multi-path, to avoid inter-symbol interference when the signal goes into the deep fades, so the cyclic prefix added at the front of the signal to avoid this multi-path interference problem, how the spectrum is going to change. It's a very good tutorial paper. You can download from IEEE to look at the variations of OFDM. Okay, so with this, I'm concluding my talk on orthogonal frequency division multiplexing, the basics of orthogonal frequency division multiplexing, and how we have avoided the inter-symbol interference and interband interference, inter-channel interference between the two OFDM symbols with the mathematical explanation. So I thank the organizers for giving me this opportunity. I'm handing over to the organizers. So if you have any doubts, please let me know. And
Thank you, Ma'am. Thank you for joining with us. It was really informative. Thank you, Ma'am.
so am I on time? In time?
Yes, Ma'am.
Okay.
Thank you, Ma'am.
Okay, thank you so much. So I'm leaving the session.
Yes, Ma'am. Sure.